And we are going to proceed to what we call factorization. So factorization is a process to express a matrix as a product of two or more matrices. Factorization 的意思就是说，把一个 A 矩阵做分解，那分解成的结果呢，会是 A 矩阵等于某两个矩阵的相乘。那我们看到的是第一个 factorization 是这边写的 LU factorization。那除了 LU factorization 之外，另外还有QR，然后 LL transpose factorizations，有好多种分解法。那这些分解法呢，其实在应用上都是还蛮有用。那我们先从 LU factorization 开始。So we will start with the LU factorization. Among other useful factorization, including LU factorization, QR factorization, and LL transpose factorizations. And the process of factorization can be treated as pre-processing of a data in this matrix. And we will reorganize the data into several parts. And then the structure are useful in some way, and then perhaps more accessible for computation, like easier in computation. Like the LU factorization has its benefit in computational efficiency. So computational efficiency is actually an important issue. So even though we do not feel it when we are doing it by hand，当我们用手算的时候，我们可能感觉不出来，因为要多做一个 factorization，怎么好像变得比较复杂。But in reality, when we do the factorization and the size of matrix becomes large, the factorization actually has a computational benefit. Later, we're going to show like why LU factorization has benefit in computational efficiency. Efficiency means 效率, so that means we can compute things in a faster speed. And so at first, we will assume that A is a n by n matrix, and then that can be row reduced to echelon form. And some student mentioned that he or she is still not that clear, like what the echelon form is. So in this example in the above, in below, this is the echelon form. An echelon form satisfies three requirements. All the non-zero rows are above zero rows, and we can check that the zero rows is the last rows, and it's below every other rows. And then the elements below leading entries are all zeros. Everything to the left to the leading entries are zeros. And eventually, it looks like a stairs. So you can check the requirements one by one and then see if a matrix satisfies echelon form. And do we need to memorize the three requirements of echelon forms? And the answer is yes, because some matrix looks like the echelon form, but it's not. So you should be really familiar with the echelon form. Okay, so if A is such a matrix, we can write A as A equals to LU. This is exactly what we mean by LU factorization. And L stands for a n by n, where n is the first part of the size of entry, of the size of matrix A, n by n. This is a lower triangular matrix with ones on the diagonal. So this is the example of this lower triangular matrix. So all the diagonal entries are ones. And then this is a lower triangular. So those stars means some value. It can be any value, including 0. but then the top right corner, we have all zeros. So this is a lower triangular matrix. And then U is n by n. So we multiply L with U, we get a n by n matrix that meets the dimension of matrix A. And U is the echelon form of A. So do you still remember how we obtain such an echelon form? To obtain an echelon form of matrix A, we use Gaussian elimination. So Gaussian elimination is exactly the method we apply to obtain an echelon form of matrix A. And there are some also remark about the lower triangular matrix. Such a lower triangular matrix, this is a square matrix, and then it should be invertible. L inverse should exist. And it's also called unit lower triangular matrix. The name unit represents the fact that all the diagonal elements are all ones. So before we go to the computational part, like how we construct L and U, we will look at like why they are useful. So it's like when A equals to LU, now we are already given this relationship. A can be represented by a product of L and U. So we back to the linear system. This one is called linear system. We're back to the linear system that we are constantly interested in. 就我们在这个linear algebra 的前半部，我们都在讨论 linear system 的解。那如果有印象的话，我们会一开始讨论解的存在，然后解的唯一，等等的问题，然后呢，用各式各样的方式去表达什么样的情况，解是存在的，什么样的情况它解是不存在的。有时候会用到一些子空间的概念，例如说 span 等等不同的概念去描述，让这个 linear system 它是否存在解的这个议题呢，变成更加立体一点。那我们把 A 用 L 跟 U 来取代，然后把 U 跟 X 视为一个群体，把 U 跟 X 用一个括号把它括起来。We replace A by L and U, and then treat UX as a unit. So we use a parenthesis to put UX inside. And then we replace UX by Y. We write Y for UX. And then we can find the final solution X by solving the pair of equations. First, we solve Ly equals B. So L is the result of the unit lower triangular matrix of LU factorization. And Y is unknown. Unknown in the first linear system. So this is still a linear system, even though the matrix we are working right here is L. But then it still satisfies the format that we are multiplying matrix L, and then times some unknown vector Y equals to some known vector B. And then we solve for Y. Solve for Y vector. And after we obtain the y vector, we were going to solve the second linear system. And this system is also a matrix times a vector equals to a vector. And the second linear system is u times x. Now x is the unknown. This is unknown. And then equals to y. But y has been solved in the process of the first linear system. So now it becomes also the second linear system, and then solve for x. So eventually we will still get a solution for x, but using two linear systems. And so is it a beneficial process? Like why do we, instead of solving like one single linear system, ax equals b, and then solve for x directly? Well, there must be some benefit, otherwise we don't bother to introduce such a LU factorization and the process of solving two linear systems and then solve them 2 times. So what can be the possible benefits come from? What are the reasons that these two linear systems turns out to be easier? And it can only come from the structure of matrix. So A matrix is any matrix, but we already know that L and U has very special format. Like U is an echelon form, so it must have zeros on the top bottom left corner. And L is also a very special matrix, because first the diagonal elements are all one, and then all the top right corners are all zeros. So you know that if we are like do the computations to solve for Ly equals b, this is Ly equals b, then there are a lot of zeros right here. That means that the calculations should be easier. Whenever we check, there's a zero, and then the product directly becomes zero. And for the same reason, we have ux equals y, and all the bottom left corner, 左下角, bottom left corners are all zeros. So when we do the multiplications, when we meet zeros, the result is zero. So that's why that solving these two linear systems has a efficiency compared with the one single linear system. And if we want to show what's this mapping about, initially we map x to b from the domain to the codomain. Then that means that we are multiplying, left multiplying x by a, and then that equals to b. And now we're having some intermediate stop. Intermediate stop is like we have 2-segment itineraries, and then there are airplane going from one origin to the destination. But then there is a stop in the middle. And this stops like multiplying, sorry, starting from here. left multiplying y by L equals to B, and then left multiplying x by U equals to Y. And that will give us the same result of the AX equals to B. The same X, the same X will be obtained right here. So here's one example. Suppose we are given a matrix A right here, and we can verify whether this two matrix is L and U. So we need to check if this is the echelon form. And can be verified. You need to actually perform a Gaussian elimination to find out that if this is the echelon form with the pivot positions on the fourth columns, and all the bottom left corners have 0 values. And also for L matrix, all the diagonal entries are 1. And then the top right corners are all zeros. And then we can do the calculation quickly, like 1 times 3 plus 0 times 0, 0 times 0, 0 times 0 is 3. So we get a 3 here. And then for the second entry, that's 1 times -7, and then 0, 0, 0. So that's -7. And for the third and the fourth, we know that because all the values right here are 0, so we get -2 and -2. And so we can quickly check the product result will be equal to this matrix A. And then we can use the LU factorization to solve AX equals to B, where B equals to this thing. So we are going to first solve Ly equals B. So this is in order to solve Ly equals to B, we form the augmented matrix by putting the B vector on the right hand side, versus the matrix L. And then we can do the Gaussian elimination to find out the row equivalent matrices, where all the values right here are 0. And then this result will give us value of y right here. So y becomes this column, -9, -4, 5, and 1, this y vector. And then we will again put the y right next to the matrix U and form the augmented matrix. This time we're going to solve Ux equals to y. And then to solve for x, we make the process of forward row reduction. And then make this part being all 0. And in this situation, this vector is the solution x. Okay, so now x is this value. We obtain x. And here are some analysis about the process. Basically, it says that in the process, we should experience 4 divisions, 6 multiplications, and 6 additions 做了4次的除法，6次的乘法，还有6次的加法。So and 要找到 x to find x, we actually use 28 operations, arithmetic operations. So what arithmetic operations mean? It means either addition, subtraction, multiplications, and divisions. So those are included in these 28 arithmetic operations. Here is a comparison. In contrast, if we do ax equals to b directly, there will be 62 operations being needed. Like because we do not know whether some positions has 0, so it means that we will need to like actually enumerate and go through every single elements to find out the to find out whether that value is a non-zero value or 0 value and then record it. But in the LU factorization, the benefit is what we mentioned earlier. We already know that at some fixed place, the values must be zeros in either in the top right or the bottom left corners. All those values right there must be 0. So everything times zeros will become 0. So we can directly skip that process to check to do the multiplications and also unnecessary additions. 不需要的乘法跟不需要的加法就不需要在2阶段的线性系统的时候再重复的去做，所以我们可以省掉很多算术上面的运算、加减乘除等等。Okay, so now we're back to another key issue, like how do I find out the L matrix and U matrix, even though I know that I can use the L and U matrix to do 2-stage linear systems. And I already know that U is the echelon form. U is the echelon form obtained from the Gaussian elimination. And so here's the process to identify such a L matrix. So since this A matrix is a n by n matrix, 4 times 5 matrix, and L should be of n by n. So that's exactly the numbers of rows A matrix have. So L should be a 4 by 4 matrix. The first column of this L should be the first columns of A divided by the top pivot entry, because we're going to make the diagonal elements to be 1. So we divide the entire row by 2. So we obtain the first column right here of L matrix. And then okay, this is how we get the echelon form. And we can observe the process of it. Here I identify the first pivot, which is 2. And then after the forward row reduction, these places become 0. And then the second pivot entry 3 is identified. So we further reduce it and then make these places 0. And the next pivot we identify is 2. And then in the next steps, we make this place 0. And in the meantime, we identify the fourth pivot. And this is the echelon form. Looks like this. So we have 4 rows and then 4 pivot position. So the pivots we identify are 2, 2, 3, 2, and 5. And then we collect the pivot position and then everything below it. So this is the original matrix, original pivot column. So everything right here, everything right here, and everything right here, everything below it. But there's nothing below 5, so we do not need to collect it. So in the process of finding the echelon form, we collect the pivot and then also the value below it. Collect the pivots and the numbers below them. Okay, so we get 1, 2, 3, 4 columns. Only the pivots and values below it are collected. And then we all divided all of them by the pivot itself. Now we make the diagonal entries 1. And this is exactly how the matrix L is formed. Okay, so here's a summary, like how if we calculate any arbitrarily n by n matrix A. So in one of the example we see before, we demonstrate like we can actually count the number of additions, divisions, multiplication, subtractions. But for a general size n by n matrix, we can have all these results. It's like computing a LU factorization takes 2n to the power of 3 divided by 3 flops operations. This word means operations. Operation. And then to calculate A inverse will require another 2n to the power of 3 flops. And if we solve 2 linear systems, we will need 2 times n to the power of 2 flops. And then if we multiply multiplications of B by A inverse, it will require also 2n to the power of 2 flops. Okay, so then we can do the calculations, and we find out that if we have an n that's greater than or equal to 30, then the benefits of numerical efficiency is significant. Okay, next we are going to see what is elementary matrices. Even though in homework, I think you already see this elementary matrix once, but then here comes the formal definition of that. So an elementary matrix is one that is obtained by performing a single elementary row operations on an identity matrix. So the key word is a single elementary row operation. And then where it is performed is on an identity matrix. So we're doing row operations on identity matrix. So suppose we have E1, E2, and E3, and compute E1 times A, E2 times A, and E3 times A, and describe how these products can be obtained. by elementary row operations on A. So after we do the calculations, because it's a matrix with notations, and we found out that addition of -4 times row 1 of A to row 3 produces produces E1A. So this is what we call row replacement, one of the elementary row operations. And an interchange of row 1 and row 2 produces E2A. And this corresponds to interchange, the second row operation, interchange. The first one is row replacement, and the second one, row interchange. And then multiplication of row 3 of A by 5 produces E3A. This is the third row operations. We call it scaling. Okay, so the three matrices, elementary matrices, all correspond to row replacement, interchange, or the scaling. So here it says that the resulting matrix of elementary row operation is a left multiplications of matrix A。就我们要把这个 elementary matrix 乘在 A 矩阵的左边，而不是右边。那这样把对应的 elementary matrix 乘在矩阵的右边的意思，就可以把它翻译成说，我们现在对 A 矩阵做了row replacement， 或是我们现在对 A 矩阵做了 scaling， 那就取决于你在左边乘的这个 E 矩阵长的形状。Okay, and there are some properties. Each elementary matrix is invertible, so it must be true. 那为什么是 invertible 呢？因为所有做的，之前我们有提到说 invertible 的含义是 undo， 就是我们不管是做线性转换，那这边是做 row operations 也一样，就是可以把你做的刚刚那个动作再还原回来，所以只要是它可以还原的，就可以 undo 的，那么这个矩阵，你可以尤其是在这种有图像的操作的时候，我们就是就会说它总是 invertible。那么 row operations 是可以 undo 的吗？ Is row operations reversible? And the answer is yes. Whenever you can, we call it row equivalence. Last time we defined it. So when you are able to reduce using the forward matrix reduction, you are able to reduce the matrix into an identity matrix. It means that there exists another way that you can, starting from an identity matrix, but using row operations to retrieve the original A. So this process can be undo, like you reduce it first, and then you add values to it, or do the scaling, and then you are able to construct the matrix A. So it has a relationship that we say that each elementary matrix is invertible. Okay, the inverse of this elementary matrix transforms E back into identity matrix. So if we have an A matrix, and then we want to do some row operation on it, it means that we are multiplying it on its left-hand side by a matrix E. And if we want to undo it, it's like we further multiply the E inverse to it, and it means undo. And this E means row operation. Okay, matrix. Okay, and everything you want to operate, you need to multiply it to the left-hand side of the matrix. 就是要对某一个矩阵 A 做一个操作，那么必须要把这个矩阵乘在 A 矩阵的左边。那就好比说，我们说，如果我们要还原 A 矩阵，假设 A 矩阵本身是一个 linear transformation， transformation。那么要 undo 这个 linear transformation，我们就是左乘 A inverse，那它的意思就会也是 undo。Okay, then next we can, in this example, we are asked to find out the inverse of elementary matrix. So since this is an elementary matrix, in order to, okay, we can first analyze what it means. Okay, how do we reverse the order, like undo the things we have undo the things we have done on the identity matrix. So we are going to transform E1 into identity matrix. Again, this is undo action. So we should add 4 times row 1 to row 3. So that can reduce this part, and then that makes this thing 0, and then that will bring E1 to identity matrix. And that row operations means exactly the inverse of E1. So inverse of E1 becomes this one, where the first row should be multiplied by 4, and then add to the third row operated on identity matrix. So you do not really need to use the Gauss-Jordan method, which is to, if we want to compute E1 inverse of E1, we can use the forward row reduction until the left-hand side becomes E1, and then the things appear on the right-hand side is E1 inverse. But here, this is special because this is elementary matrix. So we can use the meaning of it. Use the meaning of elementary matrix to compute E1 inverse. Okay, so suppose A can be reduced to echelon form U using only row replacements. And there exists a unit lower triangular elementary matrices such that we can write A and then running a series of row operations. A series of row operations. And then according to its order, the first one, the first row operation we made on A is E1, and then E2, E3, until EP. So suppose there are P row operations being executed, and then the result is U. We put U on the right-hand side of this equation. Then we can use the notation of inverse matrix, which is A equals to this, treat everything as a bunch， 把所有的 elementary matrix 相乘，把它视为一个单位因为矩阵相乘还是矩阵嘛。然后等号的左右同乘以这个单位的 inverse。那左手边因为单位的 inverse 乘以单位自己就变成 identity matrix， 所以就不见，只剩下 A 自己。然后呢，右边则是这个括号里面的东西，它的取 inverse 之后乘以 U。那因此呢，这件事情我们又等同于 A 等于 LU， 把它 A 等于 LU 写在这边。其实我们就发现说，这个单位的东西 inverse 它就会等于 U， 就等于 L。 所以我们就发现说，哦，原来 L 它也有一个表达式。当然，我们用前面的那个数值，就是找到 pivot 跟 pivot 以下的 value 就可以构成 L。数值的做法是那样，但它的 expression 是这样。它其实是一组 elementary matrix 相乘，然后再取 inverse， 而这个东西是 always 存在。我们刚刚说，因为 elementary matrix 这个 row operations， 它是 always 可逆，所以这个东西永远存在 ，always exist， 就不用担心说，哎，这边写了一个 inverse， 但是有没有机会说它的 inverse 算不出来的？不会，是保证算得出来的。Okay, then it can be shown that products and inverse of the unit lower triangular matrices are also unit lower triangular. Thus, L is unit lower triangular. And okay, so here's like just a systematic way to do the LU factorization, but it should be exactly the same as what we had in the example. So you may just take a look at the text description. 文字叙述可以就是稍微看一下就好，因为真的计算方式跟之前那个 example 是一致的。第一步是 reduce A to an echelon form by a sequence of row replacement, if possible. 那第二步呢，则是place entries in L such that the same sequence of row operations reduces L to identity。那这个步骤呢，就是等同于把这个地方把这个位置把它算出来。对。那矩阵相乘的 inverse 大家有一个印象吗？就是说它的如果要把它写成 inverse 的话，比方说我这边相乘的 inverse， 它必须要等于它的 order 要反过来就是 E1 inverse， 然后 E2 inverse， 一直到 EP inverse。OK， 那么用这种方式呢，就可以算出 L。Okay, so we're done for today's lecture. Do you have any questions?